Okay, right. So like a few hours ago, I voiced some of my thoughts on projection matrices, and I realized that the ending was a bit I was kind of running out of steam, so I kind of just stopped a bit prematurely. But I was actually looking at the video I just did. Like I'll like replay at 102:42. Wait. I wanted to show that so that's it. So what is P again? P is the projection of B onto the span of all the AIs, and that we've just kind of like this. So P, like I said, is the projection vector when you project B onto the span of the AI. And what I want to do is I want to show that if the columns of A are orthogonal to each other, that is AI.aj wherever I is not equal to j equals 0. That's what like mutually orthogonal, like my interpretation, that's what I think it means. I mean that's what it means. So like what I want to do is show that this P in this special case where these AI basis vectors for span of AI, like for span of all the A's, I want to show that the projection P can be like kind of decomposed into the sum of B projected into all the AI. But the problem here is that I'm kind of, instead of B, I'm actually using P. Like I'm kind of defining it in terms of itself recursively, which is not desirable, right? And actually, like towards the end, like I kind of like already know what the fix is, and like for a few seconds I kind of present it and I kind of hand wave over it. But I would like to take some time to like formalize it, but I'll continue. Means that it can also be expressed as the sum of like, okay, so technically we don't want this P here, we want it to be B. Exactly. I just realized my mistake right around this time mark, 103. But like we know that P, like B equals P plus E. And like whenever we like do a dot product, like whenever, okay, I drew a minus sign, but basically the point is that like B and P, when we, in terms of like the projections onto A, like B and P basically are like, again, like we can kind of discard the E, so like B and P are kind of like become each other from the perspective of the AIs. Like P plus E, right? Yeah, P plus E. But whenever we do any AIs dot P, right, like necessarily like AI dot B equals AI dot P, because like everything else zeroes out. Basically, I'm taking this whole thing and I'm just kind of doing the familiar pattern of just dotting both sides by A. Actually, I think I'll basically stop right now, but okay, so he stopped, I'll continue. Okay, right, so here I was, right? So right now we have this, right, equals to P, right? But we want to express P in terms like P is the projection of B onto the span of all the AIs. Now B equals PE, so like we can reshuffle that as P equals B minus E. Just some squiggly nonsense, and let's substitute that inside here and here, right? So now this equals the sum over all the AI, over I, of AI dot B minus E, right, over AI squared times, this whole thing is a scaling factor for B minus E, right? Now, what we can do here, right, is we can kind of distribute this this dot product. So like this equals summation over I of A, at least I think we can, dot B over A I. Now this is the part we really want, because like we're basically building up to like projecting B onto the AI. the ith basis of a span of AI. Well, you know, AI. I'm sure we know what I'm talking about. Plus AI. Again, we're distributing across from here, and that's just a constant, like 1 over AI squared. Like that's just the, like, just a constant that we're dividing by, so we can just, like, it's not a big deal. AI dot E, right? Over, I mean, I already know this is 0. I'm just writing this for formality, just to, like, show the distribution. Just to, like, kind of show all my steps. But, like, and this whole thing, right, is a scalar. And we're scaling B minus E. Is P. Right? But AI dot E is 0. So this whole thing goes away. So P equals the summation over I of AI dot B over, wait, I forgot the square, right? AI squared B minus wait, what? I just wanted this. I was hoping this would 0 out. Let me just go a bit back, see where this thing one came from. What am I doing? Okay, so P, right? We know, so then, like, this P, which is the, like, the projection of B onto the span of AI, is a weighted sum of all the AI, right? Like, surely that's fine. And then for each, we can kind of apply AI, just A1 here, just any AI, we can dot product that on both sides. In this case, like, A1 dot P equals W1, and then AI squared, yep, and then everything else zeroes out because we're assuming that all the AI are an orthogonal basis, or orthogonally, linearly orthogonal to each other. Which means that Wi can just be represented as AI dot P over AI squared. Okay. So then we're just, like, plugging that in right there. So that's the Wi. Oh! So this thing here, Wi is this, but this is AI. I don't know where the hell this P came from. Shit, okay, fine. Let's just get rid of all that junk. Yeah, I don't know what I'm talking about, right? So this Pi, right, let's say this P, right, is represented as a sum over I of Wi AI, right? That's important, right? And now we just take this Wi, we plug it in there. Okay, I guess I was really tired in the end of last video, so I'm really sorry about that. I mean, I'm glad that, like, as I was working out, I realized that, like, I had some misgivings about it. But anyways, let's rectify my mistakes. Really dumb mistake. This A looked like a P. I don't know how I got that. But anyway, so P is the sum over I of Wi AI, like just taking this and writing in the more compact summation notation. And then we kind of, and then by using this trick of, like, we're exploiting the orthogonality of all the bases of all the AIs, of all the AI, because like A1 is orthogonal to A2, like AI is orthogonal to AI.aj equals 0 in the case where I is not equal to j. Right, so we can use that, and like we can take each like AI, all the AIs, we can take this expansion form, like P equals the expanded form, and we can just dot product by AI on both sides, and then that basically zeroes everything out. So then like we can use, so again, we dot the dot stuff, we zero all the terms except for the ith term, which so we got this, and then we solve for like, we use this to solve for wi. Now we plug it back into here, and what we're going to get, which I'm going to hopefully not screw up on again, is this wi, which I'm going to write here, ai dot p over ai, and this whole thing squared, and then this whole thing is a scalar, not for p, because that's recursive, but instead, I mean, not for p, but for ai. For AI, right? Great. Okay. So what does this mean here, right? So AI.p is kind of like, so AI.p kind of gives you some information of like p projected onto AI, like the length of that times AI, the magnitude. So like AI.p is will give you the length of the projection of pi of p onto AI, also multiplied by the magnitude of AI, but then we're dividing by that twice. So like one set's cancelled, and that's the norm. So this basically right here is basically saying, like the 1D case, which we derived right here, right? So again, if we replace all the A's with like AI, right? Then like this thing right here, right? So this is the 1D case where we're just projecting B onto A, right? Similarly, this is the same thing. Well, where am I? Yes. So basically, the thing inside the summation is basically like this whole thing right here represents a vector, namely the projection of P onto A of I, right? But then we're defining P in terms of itself, and that's like just recursive. So instead, we're going to do the same thing. Recall again what I was trying to do here, right? B equals P plus E. E is like the error, the offset. So then P equals B minus E, right? So then we're just going to like use the fact that P equals to B minus E. Yes, I know I stopped doing the squiggly vector things. I mean, I think by now we all know which terms are vectors, which are scalars. So then by plugging in B minus E, right, and then eventually we're going to leverage the like this orthogonality of A and E. So then we we expand this out, right? So now P equals the summation over I of AI dot B. Finally, we're projecting B onto AI. Very nice. I'm glad to see that. Like what I've just written so far is it kind of looks like it's resembling the projection of B onto AI. This whole thing times AI, right? Minus AI dot E, which we know is 0. We know this whole thing zeroes out eventually, right? Over AI squared. This whole thing AI. Wait, is that correct? And then since we know AI E is 0, then this whole thing zeroes out. So is this correct? AI dot B minus AI dot E. But did I skip too many steps? Let me just try it again. AI dot B minus AI dot E, this whole thing, or some constant, let's just call that whatever, C, where C is AI, the whole thing squared, times AI, scaling AI, and then basically, yeah, we just kind of do like split that out as AI dot B over C minus AI dot E over, well, we know this whole thing zeroes out anyway, so we're left with AI dot B over C AI, where C is this bottom thing, right? So indeed, this thing, right, we got is correct. So now, what this is saying, right, is in the case that all the AI are orthogonal to each other, P, which is the span of some vector B projected onto the span of AI, right? So P is let's go back to this image right here, where we have oh, I forget, I'll just draw it out again. Or, well, yeah, so like we have like A1 and we have like A2. Well, sorry, let's just make it A2. And yes, these are perpendicular to each other, A2. And we have like some B. Then when we project B, right, onto like, let's say, again, A1, let's just go A1, let's go A2, right? So like this coordinate right here is basically like A1 plus A2. Like that's like our desired P, right? Our desired like P again. So like this is P. It can be written as like it is some multiple of A1 plus some multiple of A2. In this case, it's one of each. Like go A1 and this step A1 this way, and then step A2 that way. Or commutatively step A2 and then step A1, right? It's just P equals A1 plus A2, right? Like that's kind of like what we're doing, right? And this P, right? This P, which we have here, this P is the span, like this is B. Like this P is the projection of B onto the subspace given by all the AI, the span of the AI, right? And then in the case where all the AIs are orthogonal to each other, then we can actually decompose this and write this in terms of sums over I of the projection of B onto those AI, and then sum them all up so that we each get like the ith contribution, just sum them over the i's, and we get the total, and we get this vector P that we want. And just kind of visually, right? Like if we have like if we just have like an x-axis and a y-axis, right? And then we have like some z-axis, right? And let's just take some vector, like, so let's say we have it in the form of x. All right, that's not an x. We have it like in the form of x, y, z, right? Let's just take like 1 of x, 2 of y, and 3 of z. 1, 2, 3, right? And that's z, right? So it's like, that's 1. We take 1 step here, 2 steps here, right? And then 1, 2, 3 steps here, right? So like this dot, like from here, if we draw a line from here to here, that will give us this point 1, 2, 3, B, right? So like that's kind of like our B. It's the arrow, like the tip of B. The head is from here to here, right? If you project it onto XY, it's clear that like this is our P. Like this is our 1, 2, 3, and like that's our P, right? So P, pretty obviously, if you like take this B right here and project it down onto X and Y, this vector right here from like 0 to here, P, is simply like its x coordinate is 1, its y coordinate is 2, and its z coordinate is 0. Because like z is basically like kind of like the E, the left null space. It's perpendicular to the xy plane. It's like that perpendicular stuff that we have to kind of squash out, zero out. So if you look at this original B, right, as 1, 2, 3, and we look at this P as 1, 2, 0, like basically to project any B in the form of x, y, z onto the xy plane, that basically kind of, after we apply the projection matrix to it, like PB to it, then we're going to get x, y, 0, right? And then 1 and so x and y actually, in fact, are the projections of B onto the x-axis, right? If you look at like how B projects onto the x-axis, it is just this, 1. And then how B projects onto the y-axis, it's just 2. Like, that's pretty, yeah, that, I mean, you can think about that yourself, but like, that's it. In fact, one final exercise before I wrap this projection matrix stuff up is, I'm gonna say that like in this xy case, xy is like this like kind of unit vector case. Let's actually work it out here. Like let's actually show that xyz gets to xy0. Again, this is our main result, right? So now let's compute this for a being what? Just like I hat and j hat, right? 1, 0, 1, 0, right? So like let's let this equal a. And then what we're trying to do here is we're trying to show that xyz becomes xy0, right? Okay. So, yeah, let's do that. A, ATA, AT, okay. A, let's see if I memorize this correctly. A, ATA, yep. I mean, I can always rederive it, but I'm sick of deriving it. AT, A inverse, this whole thing, inverse, AT, that is P, right? And we want to solve, we want to take, and what we want to do is show that P applied to x, y, z. Oh, sorry, I forgot. It's not 2 by 2. A is going to be equal to, it's a 3D case. We're going to have 1, 0, 0, and then that's our x, I hat, and our j hat in the 3D case is 0, 1, 0. So this is our A. Right? So let's actually work this out. We want to show that P of xyz equals to just xy0, y0. And if that's true, then we've just shown that like we've kind of shown a nice example of this neat decomposition of like B onto P, right? Like xyz onto just the xy plane basically like becomes a sum over like the x and y directions of B onto the x-axis and then B onto the y-axis, because AI like AF1 would be the x-axis, AF2 would be the y-axis in this case. So like indeed, like if we can show this, which kind of it's clearly like visually pretty obvious, like if we have xyz and we project onto xy, we zero out the z components, we're left with like projection of B onto x and then projection of B onto y, and we just sum them together. Like we go here, take a step here, take a step there, and bam, that gives us P. But let's just like wrap it up by like actually computing this to like kind of show that this wonderful projection matrix expression that we derived is actually kind of checks out for this case. Okay, so then I've actually not done matrix multiplication. I mean, I've actually not like done computations in a long time, but okay, let's do AT, right? So AT is what's the row? The first row is just the first column, right? 1, 0, 0, and then the second row is 0, 1, 0, right? So we want to solve like, so then what is so what we want to do is we want to like compute P of xyz. So let's stick xyz in, right? X, Y, Z. Okay. So it's like kind of question mark, is this equal to xy0, right? Okay. So we start off from the right hand side, like kind of first do this. So what is AT applied to X, Y, Z, right? So X kind of goes to this column, Y goes to that column, and then Z goes to the 0 column, and then we sum them all up. So that would be, so like this thing, what we would get is the first column of this, would be like, we dot product X, Y, Z with 1, 0, 0, we just get X. And then we dot product X, Y, Z with 0, 1, 0, and we just get Y. So like right here, we just get X and Y. And now ATA, the whole thing inverse, well, we actually know that this is gonna like cancel out, actually. I've already shown that earlier. Like, what is ATA, right? That's kind of, we know it's gonna be the identity matrix, but I'll just show it again just because I feel like it. Right? ATA 0, 0, 0, 1, 0. Okay. So here it would be I3, like we'd get like identity matrix in the third 3x3 case. But anyways, so 1, 0, 0 dot that is just 1 here. Then now let's solve this one. So 1, 0, 0 dot this one. So like 1, 0, 0 dot 0, 1, 0. Well, everything is just kind of zeroed out, right? And then okay, oh, it's a 2x2 case. What am I saying? Yeah, it's a 2x2 identity matrix because we have A1, A2. It's I2 and I3. And here, this entry here, 0, 1, 0 dot 1, 0, 0, everything zeroes out. And 0, 1, 0 dot 0, 1, 0 is, well, 1. So ATA is identity matrix. It's inverse identity matrix, so we can just kind of get rid of that. So we're just left with A, right? As 1, 0, 0, and 0, 1, 0 of XY. Yeah, I guess this example, like, it would be nice to actually see this in play where, like, the A1 and A2, like, these two aren't mutually, orthogonal. But I just wanted to, like, I really want them to be orthogonal so I could kind of, like, give insight, give, like, an intuition onto, like, this really elegant decomposition of P, like, where, like, B onto that is just, like, B onto each of the AI summed together. So okay, let's compute this. X weights this column and Y weights this column. So we're just like kind of like X of X applied to 1, 0, 0, and then Y, which weights plus Y onto 0, 1, 0. Yes, this is a different formulation of matrix multiplication, but they're all the same thing. And what we're gonna get ultimately is just X here, and then second, like the first is like just x1, y0, like again, x1, y0. That's how that's why it's dot product. Here, x0, y1, right? Like here, like this would like x0 and then y1, and then that's 0, 0, that's just 0, right? So indeed, we have shown that this P applied to x, y, z ultimately gives us x, y, 0. So projecting any x, y, z vector onto the xy plane, like where like that's the A, indeed zeroes out the z. So I think that kind of wraps up this projection matrix. Okay, great. Now, in fact, I have this folder in my Google Drives called like Math Insights, where like a few years ago I started like kind of reviewing lots of undergrad math classes. In fact, I have like something similar for CS too. But like I've actually been kind of like, before presenting like what I'm doing right now, I've actually been looking at them. For example, like intuitive projections or orthonormal vectors, which is like what I just did like the previous live stream and just now. Basically is kind of like exactly what I kind of did right now. And then now what I'm going to do is like this thing, null if A, that's what I'm about to do. And again, for previous live streams, like dot product projection relationship, in fact, I've actually done, like, that was like my first live stream for this, and like, yes, like I drew a really nice diagram, which I tried to do like the first screen, but like I kind of dotted the A's, and then I got like I kind of drew like this vector here. I kind of like drew it parallel, and I kind of like did that, and I kind of did this. Like I ended up doing something similar, but here I drew like a really nice parallelogram showing that like decomposing a dot product into like the x's and the y's contribution is like this, and that gives you the whole projection, like the linear combination. Anyways, I'm getting off topic. Let's just kind of go here. So like here's what I'm trying to do right now, right? So like we have this very wonderful result, right? This thing, right? This projection matrix A, and then in parentheses ATA, the whole thing inverse, like ATA, the whole thing inverse, and then you have like A parentheses ATA and parentheses inverse, the stuff that was in the parentheses, and then AT, and like that whole thing is your projection matrix, right? And we apply that to any vector we want to project it onto the span, the column space, the range, whatever you want to call it, column space or range of A. All right, that's our projection matrix. Now, it's crucial that this ATA -1, like not all matrices we can invert. You can only invert a matrix if all the columns are linearly independent. Now, what we want to show is that like the crucial thing right here in this projection matrix is ATA, like we have to take that, like is this invertible, right? Invertible, right? Like that's what we want to like kind of understand, like when it is and when it isn't. And it turns out that this is invertible. AT, let's kind of move it here, is invertible if and only if A is invertible. A is invertible. Invertible, whatever, you got the point. Only if A is invertible, only if A is, just is, because is kind of implies invertibility. So like one way of doing like showing this, which like the book by Strang uses, Strang, what's his Gilbert Strang, like his book uses, is it basically like it says that like it shows like this statement by saying that null, the null space of this ATA is in fact the null space of A. Now, why is this like why are these two statements like one and the same? Like why are these like kind of biject? Why are these like equivalent statements? Well, from the rank nullity theorem, I mean, that could be an exercise left to the reader. I really like the way that, I mean, this is like fairly obvious, but like, this like equivalency, like if you can show this null equals null of like these two, if you can show the null spaces of two matrices that are equivalent, like, and like how that relates to this, I'm not going to explain that, or I might do it afterwards, but now I just want to focus on deriving this, right? So like there's two directions, right? Like if you have a vector in null of A, then clearly it's in the null of this ATA, right? Because if x is in null of A, null A, I feel like the more tired I am, like the sloppier I'm writing, null A, then it's obvious, like that's one direction, it's obvious that we want to show that x is in null of ATA. Writing this trackpad is so annoying, right? So this is pretty obvious because like if it's the null of A, then AT or AX, sorry, this is X not T, AX equals 0. So then you have AT A x question mark is it equal to 0? 0 vector. Well, we know that a of x equals 0. And then, so we have indeed that at applied to 0 is indeed equal to 0. So we're done. That's the very simple thing. But now we want to swap it. We want to show the other direction, right? Now we have like x is in null of a t a, and we want to prove this other direction, that this implies that x is in the null space of A. And if we do that, then we've shown both directions, and we have then completed the statement and therefore completed that statement. So then the way basically both my proof, like the way I proved it, like basically this author kind of like shows this, like this author Gilbert shows like his proof is like extremely elegant, but like I would have not come up with it. In fact, I came up with like alternative proof that actually reduces to his proof, but like here's what he does, right? First direction is trivial, reverse direction is harder. So like the book and the video lecture come up with the solution. ATAX equals 0. So like I'm first presenting his method. So x is a null space of ATA. That means ATAX equals 0. That is what that's what he is saying. I mean that's what this thing right here actually means, right? It's the null space, right? Now what he does is he takes both sides of this equation, he multiplies both, he applies A transpose, he dots both of them from x, like applies xt to both sides. Now how this happens, like I would not have figured out. So like he calls it a trick in his lecture. And my goal, I'm going to actually kind of show motivation for it after this, but he applies that, right? So then, okay. Yeah, I'm just copying his method shamelessly. So like we have xt a t a x, right? We just kind of stuck in this AT, and then xt applied to 0 is just going to be 0, so we might as well just leave that there. Like that's just 0, right? We're just taking this and making it extra complicated. But then we just happen to use the fact that xtat equals axt. Like that's just like a property of transposition. axt. So we're going to use fact, like we know, well, he knows that it's like this thing right here ends up working out to be a axt. This is like some like specialized linear algebra knowledge that I don't have, or maybe I can derive this clearly. So that's ax equals 0. But then if you look at this just means like ax is dotted against itself, right? This is basically saying that like if you dot it against yourself, this is basically saying that the norm of this squared equals to 0, right? So like the only way this is true is the only magnitude, like basically like this whole thing implies that a of x must be 0, because if a of x weren't 0, then then it would have like the norm would be a non-zero number, and that when we square it, we'd get non-zero. Therefore, ax equals 0, which indeed checks out that a is a null of A, right? Okay, but that did not make me very satisfied. I was not satisfied at all about this. So what I ended up doing was a proof by contradiction. So to show this, right? To show this thing, let me just delete everything here. Or no, I'll leave it there. I won't delete it. So to show this, what I want to say is like the reverse direction. Let's assume that x is not in null of t of a. X is not in null of a, right? If I assume that x is not in null of a, so if a implies b, then not b implies not a. No, sorry, what am I doing? Okay, so the point is, I want to have a contradiction. I want to say that x is not in this, but x is in that. That's what I'm trying to go for. So if x is a null if like this modified version ATA implies that x is a null of a. So then I want to show that like we can never have it be that x is not in null of a, but it is in null of ATA. Okay, let's just say that x is not in null of a, right? So x is not in null of a, what does that mean? That means ax is not equal to 0. That's what it means. So if we have x that is in the range like of a, that if this x is not in the null of a, let's say that we can find such an x, and let's say that that same x is in the null of ATA, then we have a contradiction, because if this statement is true, then by virtue of this x being in null of ATA means it's in the null of a, but that's contradiction because we said x was not in the null of a. So that's what we're trying to do. The overall strategy is to say that like we found x which is not in null of a, and then we're going to say that we cannot reconcile that with x being in null of this. So how do we do that? Well, okay, so like one case that's very easy is let's just say a is simply like, this is like one thing which I do, like which I personally did when I tried solving it. Just like let's just say a is just simply like one column vector a1, right? Then x, so then what is a of x? Then a of x, right, which is like x is not in the null space. A of x is simply where x is actually just like a 1 by 1. X would have to be a 1 by 1 number. It's called x, like x. So that, like, it's just actually kind of a scalar, but like a 1 by 1 vector. Not a, yeah, 1 by 1 matrix. So a applied to this vector, 1 by 1 vector, ax would give you x a1. Oh, I'm so used to ai. X a1, right? I can actually get rid of the parentheses around here. Just ax equals to x of a1, right? That should be obvious. Like x is not in the null of that. So then ax, and then so then ax is not equal to 0. So ax is not equal to 0. That means x is not equal to 0 and a1 is not equal to 0. Well, a1 is clearly not equal to 0. So we have we have that like x is not equal to 0. That's kind of self-evident from my updated connection restored. Okay, it's not equal to 0. Okay, so we have ax, right? It's not in the, so it's not in the null of a. Okay, so then this x, we want to like try to see if like we want to kind of we want to like say that like we want to say that x is not in the null of a, but it's in the null of this, and show it's impossible and have a contradiction. That's the idea. So okay, this x supposedly is in null of ATA, right? ATA x, again, a is just this thing right here, right? Equals 0. And we're trying to get a contradiction here. So ax, right? Ax is simply x a1. Actually, let's just actually write it out. So what is at, right? At is just a1, like that's at, right? And then ax is simply ax is just a1 scaled by x. So this whole thing equals 0. And of course, since this is a scalar, we can just actually plop this in the outside. So what we have is x, and then this is just a1, the magnitude squared, the norm squared, squared norm, equals 0. And that's a contradiction, is it not? Because x cannot equal 0, and a1 is not equal to 0. It's just a vector, it's non-zero. So we have a contradiction here, right? Remember, like, so then, like, that's a contradiction. So we showed it for when a is like just a1. Now let's try like a equals to the concatenation of a1 and a2, right? So now we have like this definition of a. And when I tried proving this, like, this is where it became a bit difficult for me. Like, when I actually tried this, I was not able to like have a nice contradiction. So, I mean, long story short, I like racked my head against this for a long time. Like, what is AT of AX, right? So, like, if you have like some X, so now X actually becomes like the dimensions change. It's no longer just like kind of a nice like scalar, like AX. It becomes like X1, X2, right? So, like, and like this case became harder. I mean, I can work it out and like kind of show you what I was kind of dealing with. So, like, AX in this case, AFX is becomes just x1 a1 plus x, okay, that plus is pathetic, plus x2 of a2, right? And this thing is not equal to 0. That's what our hypothesis is. That's what our like kind of statement is, that x is not in the null of this, right? Ax is not equal to 0. That's what it means by not being in the null space, right? So then at of ax, we want to like, so at of ax is 0. Like, that's what we're trying to find a contradiction in this. At of ax equals 0. We want to get like plug this in and get a contradiction. So again, at in this case is going to be a1, and that's a2, and ax is applied to x a1 plus, sorry, x1 a1 plus x2 a2 equals 0. We want to contradict that. So then, like, what is this, like, what's the first entry of this, right? So, like, this whole thing right here is basically x1, if you like kind of distribute like there, like, we'd get like x1 and then a1 magnitude squared, which we know is non-zero, right? That's pretty nice. But the problem is plus x2, and then this would be x2, which like x, like the first entry of this would be, I mean, this would be a1 dot a2. Oh, I have a good observation. So in the case that a1 and a2 were orthogonal, again, or orthogonality hits again, then we could zero it out. That'd be really nice. And like this, like, equals 0. So like, what I was trying to do when I first saw this, like when I tried doing it for like the 2-dimension, like a1, a2, and not just a1 case, is like, we know this is non-zero, but unfortunately, this thing could become a negative number if a1, a2 point in different directions and like kind of match that and become 0, in theory. like what if like we can't really, at least I don't immediately see why, like I can't really see a contradiction. And same thing here, this would be a x1 a1 dot a2. We don't have no guarantees on like these two terms right here, unfortunately. These kind of cross terms. If they're orthogonal, then yes. If a1 a2 are orthogonal, then yes, we could easily prove by contradiction like the statement, like this direction right here. We could arrive at a contradiction, but unfortunately we can't, right? So then, like, again, yes, we know this is the non-zero term. x2, I'm just writing this out for completeness sake at this point. So like it's kind of hard to like arrive at a contradiction here for me. So I kind of backed up. I really thought hard about this. And like if I had like, so like what does it mean for ATA? Like what does it mean for AT, like for any V, right? Like let's take a step back. If you have ATV equal to 0, then like what does that mean, right? And here's a crucial thing. So like right now we have AX. Well, let's call it AX. Let's let A equal to AX. Sorry, let's just let lowercase a. Let's let lowercase a equals to AX, right? And we know that like so like X is not, so like if we assume like if we start like if you say X is not in null A, and AX is not equal to 0, right? Is not equal to 0. And then A, again, I'm just kind of calling this AX A, is like A1, X1, A1. Let's make it more general, plus dot 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 plus X N AN, right? So like whatever this X is, which is not in null of A, like we do AX on it, and what we get essentially is some linear combination of these AI. In fact, I'm going to introduce this thing called A world, A's world, is the column span call of A equals the span of A1 dot 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 AN, right? So like the whole point is like when you take AX, right, and get A, so A is in A's world. That is, A is some linear combination of all the AI, right? So then that is AX. And then we have here that like AT, we're trying to get a contradiction of AX equals the 0 vector. We were trying to arrive at a contradiction here. So this AX is just A, right? And it's in A's world. It's some linear combination of these vectors. So we have AT A equals 0, right? And AT V equal, like, so like in general, if you have some vector of V, right, AT V equals 0, like what does that mean, right? That means A, like what is the, like if you have ATV, like V is like some vector, like let's expand the V, like let's actually write it out, right? So V is like, say V1 dot 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 Vn, right? So like this vector will like kind of give us again the same dimensions as V. Like well what would this like ith entry be in this vector? Well, it would be A of I dot V just AI dot V, right? Let me just, so AT is basically dot 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 A1, right? And then like dot 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 AN. So then this would be, so that's like an N by, or sorry, that's a Okay, so then basically like, yeah. So like the ith entry, like this would be n by 1 like output, where the ith entry is ai.v. And then this equals the 0th vector, right? So what that means is v is kind of, it's orthogonal to all the AI, right? So I think you're starting to see it, right? So like basically if ATA equals 0, right? That means that A1 A equals 0, A2 A equals 0, dot dot dot, A N A equals A1 dot A, A2 dot A, AN dot A equals 0, right? Because like that's what it means to be in the null space of A transpose. And like I'm kind of if you know the fact in linear algebra that the row space and the null space are orthogonal complements, or in terms of transposition, like originally where all these AIs and A transpose in the row space were actually originally in the left null space. Like the left null space is an orthogonal complement of the column space, I believe, and then this row space is the orthogonal complement of the null space. So like we know that like if you're in one of these subspaces, you cannot be in the other unless you're like the 0 vector is a trivial exception. So we already have the answer in terms of like broad linear algebra terms. But just to like kind of like, I mean, I it's kind of coming to me, right? So like this is kind of like the heart of this proof is orthogonality, right? So like we have ATA equals 0, right? So A1A equals 0, A2 equals 0, and more generally, any linear combination of the A of all these AI dot A would be equal to 0, and then we have a contradiction. So like if you have A1A equals 0, right? Then this actually implies that we can just stick a scalar to it. Like why not, right? We can just say that like we can introduce a scale. Notice that I'm going to actually introduce these scalars, right? So if A1A equals 0, again, we know that because like if ATA equals 0, that means like the first entry in ATA is A1A, right? But we can just like scale that by like x1. So like again, we can just introduce a scalar. So x1 a1 dot a equals 0, right? We can do the same thing here. I'm basically going to build this up, right? So this thing right here, like this thing basically implies if a2a is 0, that means x2 of so we can multiply, if a2 dot a is 0, then x2 times the 0 vector is also 0. So like x2 of a2 dot a equals 0, right? And we can like do this for like any, like the ith index, but like the last one would be like dot 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 xn is a scalar multiplied by that scales an dot a, right, equals 0. And now we have like these n equations. We can actually add them all up. And what do we get? x1 a. Actually, like this thing can become, I'm sorry, so like this thing can become x1 a1 dot a equals 0. And like in general, the ith one would be just x of I, a of I dot a equals 0, and then we sum up these n equations, right? So that basically gives us x1 a1 dot a plus x2 a2 times a plus dot 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 x n a n dot a, parentheses is actually dot a equals to 0. And if you factor this all out, guess what? We get x1 a1 plus dot 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 plus x n a n dot a equals 0. But if you look carefully, you realize that that was the whole point. This whole thing is just a. So this basically means that a, its norm, is 0. But that's contradiction because this a is not equal to 0, and we're done. Now this might seem like a bit of like kind of like magical, but like the whole point really, like what like the whole kind of heart of this approach is that like this a is an A's world. Like this a is a linear combination of all these AI. Like a is a member of A's world. Of A's world. It's like some blend of all the AI vectors, right? So like when I say that like x is not a null of A, then like if we take AX, right? Like cause like we want to eventually say do ATA of X. So like if x is not a null of A, then like AX, let's let AX be A and let's call it in A's world, right? But now we have ATAX equals 0, right? So like AT applied to A equals 0. But in general, like what I was trying to say here is that like if we have any, like if AT applied to anything, V, some vector equals 0, that means that V is in A's left null space or in AT's null space. And then like this V is orthogonal to A1, A2, all the way to AN. So basically, like V is perpendicular to A1, V is perpendicular to A2, and in all the A's. And in fact, V, like because it's perpendicular to everything, like by properties of linearity, we can say that V is perpendicular to any linear combination of AI, right? But that means that V is perpendicular, or that means that V is kind of orthogonal to any blend of the AIs, but that just means that V is not in A's world. A's world. Like if V is perpendicular to A1, V is perpendicular to A2, then V must be perpendicular to W1 A1 plus W2 A2, right? So like if V is perpendicular to that and that, then these both kind of imply that it's perpendicular to this. So in general, V is perpendicular to any linear combination of them, which means that V like cannot be in A's world. So ATA is 0. That means this thing right here is not in A's world. But we already said it was in A's world, so like that's how we had the contradiction. So that's kind of like, that's like my approach. Now if you compare this to like this kind of original approach right here, notice that the first step he did was kind of like apply the xt onto everything. And that is actually, when you really think about it, like that's exactly what I did. Like this xt of at, like what is this actually doing? Like xt onto at, like this is at, like just like all the columns of A become rows, right? Like just A2, whatever. Dot dot dot. So by applying like xt onto it, we're basically weighting all these rows. Like right here, ultimately, like I took x, like a equals x1 a1 plus dot 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 x1 an. I basically weighted and then like in this kind of like thing here, like for this example, like when I said v is perpendicular to a1, v is perpendicular to a2, so v is perpendicular to some linear combination of the AIs. That linear combination of the AIs is given by w1, w2, but I could also make that x1, x2, and that's precisely what I do right here, in fact. I basically take all the AI and I weight, like the AIs in this sense are actually like the rows of AT, and like I'm basically weighting them by like x1, x2 by some vector x, and that's precisely what this thing right here is. Like when you take some matrix M, and then like typically like we're so used to like seeing some matrix and some vector here, right? Like that. But we can also like do something from the left side. We can also like take V, which is like kind of, we could be like kind of like this, but we could actually flip it to like VT would be like kind of like this, and then like M. So like just like a recap of matrix multiplication, like when you take this vector, like a matrix in a single vector, like in like just some like its length is like it's just like a one dimension here and like some dimension here, then like by like applying M to this vector basically weights all the columns. But if you do xt of this vector, then what this does actually is it weights all the rows. So basically like by introducing xt to at, we're in fact weighting all of those rows. Like if x would be like, let's say if x were a w or x1, like a 2x1 matrix, it's so messy. If x were x1, x2, then if we do, and then like, and if a was mirrors being updated, if a were a1, a2, right, just like by like that's by columns, right, then if we do xt of at, if you would do xt of at, like what is that? Well, xt of at is like, again, it weights the column, it weights all the AIs, it weights the rows of FAT. x1, x2 of again, like by transposing this matrix to get AT, this becomes A1 and A2. And if you actually work this out, like this ends up like this ends up weighting these rows, and like this actually becomes x1 a1 plus x2 a2, which is basically precisely what we were actually like, what my method was doing here. Like, yeah, I mean that's basically what it was doing. It was we were just weighting like the ith column of AI by xi. That was like kind of the strategy. And like, in fact, I have like one of these in my math insights. I have matrix left versus right mult, which is just like weighted, like left side xta returns a row vector. It's a linear combination of the rows of A, really only used to do matrix multiplication like ax. Like basically, like if you have like if we just do like, yeah, again, if we just do like mv, the v basically weights the columns of m. But if we do vt transpose applied, like left applied to m, then like this v basically spreads itself and weights the rows of m. That's just like kind of how matrix multiplication works. I mean, I could work this out just like, so like right here, right, like we take some like column here and we dot it against like this x1, x2, right? So like the first entry in this vector would be this column dot that. So x1 would hit this and x2 would hit that, right? And then in general, for some general thing, for some general slice column here, again, x1 would hit that when we dot this against this row, and x2 would hit that. So always x1 is hitting entries of a1, and x2 is hitting entries of a2. So it's like x1 is tied to the first row, and x2 is tied to the second row. And therefore, like, this indeed is true that, like, we end up weighting these rows by x1, x2. That's kind of how this xt, like, applying the vectors to the transpose to the left of this matrix ends up weighting its rows. And, like, that's precisely what we do here. Like, ATV equals 0, right? Like, we're basically kind of, like, saying that, like, this, like, in this case, like, AT equals 0, right? So, like, AT applied to anything equals 0 means that, like, this thing is orthogonal to A1, A2, like, ATV equals 0 means that V is perpendicular to A1, A2, and more generally, V is, like, we can, like, basically, like, V is not in A's world. Like, any kind of, like, any, like, linear combination of these A's, of AIs, of V can definitely not be that. It's actually, it's perpendicular to that. It cannot be that. That is, like, V cannot be any linear combination of all the AIs. But so, like, we can kind of set it up to, like, force it to be perpendicular to, like, a particular combination of AIs, like, specified by the x's, and that's where we get our contradiction. In other words, like, if you think about it in terms of, like, linear algebra, and you're aware of, like, orthogonal complements, like the four subspaces that a matrix defines, like the null space, the column space, the row space, the left null space, then, like, another way of, like, viewing this, like, another way of, like, showing this direction statement, right, this contradiction is, like, if we have AT of AX equal to 0, that means A of X is in the left null space of A. Also, it's in, or equivalently, A of X is in the row space of A transpose, right? It's in the row space of A transpose. But if you're in the row space of like, A transpose, that means the row space is the orthogonal complement of the null space. So if you're in the, like, if AX is in the row space of AT, that means AX cannot be in the null space of, cannot be in the null space of AT. But AX is in the null space, of AT, because AX is 0, which means AX cannot be in the row space of AT. But what is the row space of AT? The row space of AT is the column space of A, untransposed. But the column space, so basically, if AX is 0, that means AX is in the null space of AT, which means, because it's a complement, because null space is complement to row space, it means that A of X is in the row space. I mean, if AX is in the null space of A transpose, which means AX cannot be in the null space. Sorry, it cannot be in the row space of A transpose. But that means AX cannot be in the column space of A. So that means, if AX is 0, that means AX cannot be in the column space of A. Which means, so if AX is not in the column space of A, then, well, the only way that works is if AX equals 0. If X is null of A. Because AX means we're taking X and weighting the columns of A by X. So necessarily it's in the column space, unless, for the one special case, that AX is 0. Therefore, like, we've basically kind of shown that, like, AX kind of, like, we've basically shown that the X is in the null space of A to make AX 0, because AX is clearly in the column space of A, unless AX becomes 0, which means X in the null space of A. So, like, I'm like that's another kind of more abstract view, which is kind of like, if you kind of know if you kind of are aware of, like, the notion of orthogonal complements, that the row space is complement, like the row space of AFT is a orthogonal to the row space is orthogonal to the null space. But if you don't, I mean, like doing this like technique here, we kind of actually kind of gave some, we kind of like maybe even like derived like using these similar techniques that like this orthogonality relationship with these subspaces. But yeah, anyways, I believe that like right now, but like the overall big picture is that like ATA, like for the projection matrix to work, like this whole P here, this is the main result. And like this can work if as long as A is invertible. That is, the columns of A are linearly independent. And then when it comes to least squares, we're going to see that that's most likely the case. So yeah, I guess the remaining thing is just least squares regression. But the hard work, like the actual machinery, we've already built up this projection matrix. So I think I'll just stop here.